Hello, my name is John Kunze. I'm a computer scientist who has been working with data centers, libraries, museums, and archives for the past 20 years. This talk includes examples from each of those sectors. In case you're wondering, a persistent identifier, or PID, serves the same purpose as a permalink. It's meant to persist, but we can very rarely prove persistence, which would require extensive monitoring. So a persistent identifier, whether an ARK, DOI, handle, or any other permalink, is an identifier that was aspirationally persistent when it was created. Why should we care about ARKs? The average lifetime of a URL was once said to be 100 days. At the end of its life, a URL link breaks, usually giving the dreaded 404 not found error that most of us have seen. While that can be irritating, it's a minor disaster for memory organizations. So ARKs can serve as robust links for any kind of thing in any discipline. The ARK scheme is one of 5 so-called persistent identifier or PID schemes. There's been a great deal of nonsense written about PIDs. Some of it is described in a Twitter thread called 10 Persistent Myths About Persistent Identifiers, which is available at the link using this example ARK or the QR code next to it. PIDs are like permalinks that contain hints that they're different from the average URL link. Every URL is potentially persistent, but strangely, some people think it becomes a PID when it acquires some superficial syntax differences, such as the ARK colon in this example ARK, or when you see the domain name doi.org at the start of a URL. Syntax is neither magic nor a guarantee. It's never more than a suggestion that you might find this link to be more stable than 99% of URLs that are produced without a thought for preservation. So-called PIDs break often and by the hundreds of thousands, which is a normal part of providing a preservation service. Committed service providers will even repair some of those links. So syntax doesn't make it persistent, but it may suggest that you're looking at a permalink, whether or not it's displayed next to the label permalink. The nonsense was in full bloom in the late 1990s, but it polluted the debate about the 4 proposed PID schemes. That is why the Archival Resource Key, or ARK identifier scheme, was introduced in 2001. Here's what an ARK looks like. At first glance, it's a URL that carries this internal label. To the right, the 5-digit Name Assigning Authority number, or NAN for short, identifies the organization that created the ARK. Further right, the part after the NAN names the thing that the ARK was assigned to. To the left, the host name makes the ARK actionable, or something you can click on. It's also known as the resolver. ARKs are unusual among persistent identifiers in allowing organizations to run their own resolvers. The part starting with the ARK colon is the core, globally unique identity. It doesn't depend on the host being available or on the future existence of the World Wide Web. In the previous example, you saw n2t.net, which is a global name-to-thing resolver. N2T is the main ARK resolver, so why doesn't it contain the letters ARK? Well, one goal of the ARK design was to break out of the silos and walled gardens surrounding many identifier systems. So what got built was the name-to-thing resolver, or N2T. The domain name n2t.net is good for short citation strings, and true to its name, N2T also resolves hundreds of different identifier schemes. ARK organizations include a wide variety of memory institutions, nonprofits, for-profits, data centers, and government agencies. A few are listed on this slide. What are ARKs used for? Here are some examples. The heaviest user of ARKs is the largest genealogical research organization called Family Search International. Next is the archive of all source files for mainstream published journal content. Technically, they have over 40 billion ARKs, but apparently only 100 million of them are interesting externally. The French National Institute of Scientific and Technical Information uses ARKs in preserving datasets and supplemental information. The Internet Archive has been assigning ARKs to scanned books and texts since 2008. The Smithsonian is rapidly expanding their use of ARKs with a target of 100 to 150 million. The French National Library was an early adopter, and here's a wonderful image depicting the biblical ark. ARKs are also important for people, especially historical figures. For example, there's an ARK for the 19th century mathematician Ada Lovelace. Her ARK was assigned as part of the SNAC project, whose work some have described as assigning orchids for dead people. Here's a brief case study for the French National Institute for Scientific and Technical Information. Their reserved NAN is 67375. On the right is one of its 22 million records, in this case, an entry from the SAGE social science thesaurus. Inside the red rectangle, you can see the ARK they assigned along with its NAN. Note how this ARK URL begins with their own resolver, not with N2T. It ends with an opaque string that tells us nothing about what it's assigned to, but we can tell from the metadata in the record that it's assigned to a conceptual thing. Here's another brief case study, this time for the Internet Archive's ARK implementation. Note their reserved NAN, 13960. On the left is an example of a venerable library cataloging standard that has been digitized from paper and deposited in their text archive with an ARK. On the right is its metadata record, where you can see the ARK they assigned and its NAN inside the red rectangle. This shows what is called the compact form of an ARK, because it's just the globally unique identity without a resolver in front of it. In contrast to the identifier field above it, the ARK is opaque, which helps it age and travel well for external citation, even if it's awkward for backroom administrators. You can see a bunch of metadata above that, including 2 URN identifiers that came in with it. Best practice is to preserve all the identifiers you find. Here's an abbreviated history of PID schemes. The Perl scheme fully embraced the URL. Meanwhile, URNs, DOIs, and handles got confused for a while, at first saying that all URLs are bad, until they later reversed that position and fully embraced the URL. Turning to the inventor of the web, he said basically just use URLs and manage them carefully. The ARK approach agreed and said, go ahead and use URLs, but embed a distinguishing label to suggest that this URL is meant to be persistent and include a globally unique identity separate from the domain name and from today's web protocols. Here's a grumpy old person view of PIDs. Looking at this table, the big block of no answers in the first 4 rows tells us that no PID scheme helps you with all of the major and most of the minor causes of broken links. So why even bother? Well, some of them are free, so there will be more money to spend on the real work of preservation. This is a reminder for many of you that a core PID technique is indirect identifiers, which uses the web concept of redirects. But first, here's normal direct access. The user clicks on a URL in a web browser, which sends it to the web server appearing at the beginning of the URL, and a page is returned. With indirect access, the first server contacted says it doesn't know where the thing is, but it returns a message saying this other named server should have more information. Behind the scenes, instantaneously and unbeknownst to the user, the browser restarts the process by contacting the second server. There could be a third server, fourth, fifth, etc. This is web redirection, and it's like forwarding snail mail to a new address. Many of our ordinary web accesses involve chains of multiple redirects, all taking place quickly and without the user being aware. If you buy into the idea that PIDs actually provide value, here are some details on what they might do for you. By an amazing coincidence, this table is quite flattering to ARKs. The bottom line is always about cost. No organization pays for the right to create ARKs, pearls, or URNs in unlimited numbers. In the real world, or maybe just the academic world, PIDs that publishers use play a key role. When tenure and promotion hang in the balance, DOIs are the publisher's solution, and they are seen as a kind of badge of academic legitimacy. Pearls are free and are common in the semantic web. URNs are useful if you're a national library in a nation that subsidizes URNs. They have the unique advantage of having an internet standard behind them, even if it is frequently abused by creators of bogus URNs. Handles are popular in certain European projects and have a nicely replicated resolver infrastructure, also used by the DOI system, so they can be good if you can afford them. If you only have a couple dozen things to identify in a year, by all means, consider going to zenodo.org and assigning their subsidized DOIs. In summary, ARKs are similar to DOIs. They're both persistent identifiers for accessing content and metadata, and ARKs are found in many of the places where you'll find DOIs. In contrast, ARKs come with no fees, no limits on how many you can create, and no metadata requirements. From the beginning, ARKs were designed to be decentralized and to identify any kind of thing, digital, physical, or abstract. Finally, it is important to note that there's no conflict using both ARKs and DOIs at the same time. This is quite common. For example, you'll find a mix of both at the Smithsonian, British Library, and many other national libraries. Some outfits assign ARKs to everything, and for the subset of things that are later going to be published, they assign a DOI, where the DOI string can even be derived from the existing ARK string. Here's another use case, this one for the Smithsonian, whose NAN is 65665. I understand that the technical challenge of implementing ARKs was minor compared to getting over a dozen internal organizations within the Smithsonian to work together. You can see their NAN appearing at the beginning of each ARK. You can also see the wide range of object types, biological specimens, paintings, photos, and sculpture. Note the long opaque names they've assigned, which were generated using the UUID software that's pre-installed on nearly every platform. These unique names are long, unfortunately, but they're easy to generate. Very briefly, here's another view of the ARK syntax. It shows more detail than last time. Right now, I just want to highlight the role of the NAN, or Name Assigning Authority, number. The NAN is a 5-digit number. As such, it is opaque, which is good for longevity. But what if you want to know what's behind the opacity? Well, in a browser's address bar, you can try truncating an ARK so that it stops after its NAN, as shown in the yellow highlighting. This is a stub ARK. If you hit enter after this incomplete ARK, it lets you inspect the 12148 NAN. You can also try this with any other NANs, or you can try backing off further to a shorter stub ending with just ARK:, which tells you about the ARK scheme. You can also replace it with the name of any of over 600 different schemes that N2T knows about, such as the protein data bank. All the NAN results that you see by playing with stub ARKs in the address bar are pulled from the main NAN registry. This is just a plain text file that you can look at directly in your browser. You can use the QR code if you're interested. Here's what it looks like when you ask N2T to tell you what the 12148 NAN is. You get the record for the National Library of France, as well as when it was registered in 2005. Very importantly, it tells you where the N2T resolver should redirect incoming ARKs so that they get sent to the correct local resolver. So the NAN has two main purposes. It's a lookup key for the resolution reference point, and by defining the root of a global namespace, it isolates an organization's autonomy and responsibility for assigning its ARKs. That way, without interfering with anyone else's assignments, an organization can determine its own policies regarding identifier form, uniqueness, and reuse. Basically, just as for URLs under its domain name, an organization can freely assign ARKs in any way that it wants. Here's a link to the form you can use to request a NAN for your organization. If you want to practice using it, just indicate in the final comment that you're filling it out as a training exercise. A great deal has been written about opaque identifiers, which age and travel well. But they can be confusing because they reveal nothing about themselves to the user. One approach to soften that inconvenience is to at least make them shorter, and therefore a bit more citation friendly. The downside is that shorter IDs are harder to keep unique. One emerging trend is to use an opaque base identifier with lucid or non-opaque extensions. That can be okay because extensions are more transient than the base thing itself. For example, image thumbnails are regularly upgraded to be higher resolution. This happens every few years to keep up with evolving demand and advances in storage capacity and in network and rendering speeds. This slide lists some tools for generating opaque IDs that I won't be getting into. Back to some details of ARK syntax. The special characters slash and dot or period have reserved meaning in ARK suffixes. So that makes these characters effectively non-opaque. They help the recipient make inferences about one resource containing another or one resource being a variant of another. In any other PID or other non-ARK URL, you could guess at similar interpretations, but in ARK-based URLs, the guesswork is gone. If you use the reserved characters, you are formally declaring that these relationships exist. There's a natural parallelism between ARK suffixes and the popular IIIF image API, which is gaining traction in domains that have lots of images, such as medical research, museums, and botanical gardens. IIIF works well for addressing hierarchical subregions and variants. This leads to the next case study, this time for the French National Library, whose NAN again is 12148. Shown here is a long IIIF compliant URL. Reading the bold part from left to right, starting from the end of the opaque base ID, we can see the page number 29 under or F29 between slashes, followed by a comma-separated list of coordinates that request the return of a specific rectangular region. After that, you can see the request specifying full quality and the JPEG format. ARKs are very flexible. You can throw them away when something doesn't work out, which is much easier if you have never told anyone about them. If you don't tell anyone about your ARKs, it's as if they never happened. ARK metadata is also uniquely flexible. You can start with none, and you can add anything, such as whatever is defined in schema.org. For example, there are lots of ARKs with datasite DOI metadata. You could assign an ARK to something that doesn't exist, because in the planning phase, things need identifiers just so we can talk about them. After all, we name our children before they're born. At the moment of birth, when we've created a thing, there might be no metadata, except perhaps for a redirection target. Later, we can gradually add draft metadata, which might be reviewed and edited by others through phases of pre-release, preprint, postprint, etc. Persistence is not on or off. It is nuanced because, ironically, preservation often involves change. Valuable objects tend to be complex, human-managed clusters of digital artifacts that curators are forced to change in order to keep up with changing technical, policy, security, and legal requirements, as well as user expectations. An ARK should lead to three things. First, to the identified thing, whether digital, physical, or conceptual. Second, to metadata about it, answering basic questions of who, what, and when. And third, to a nuanced persistent statement to set expectations for returning visitors. Here's an example showing an ARK metadata request, which is created by appending a query string consisting of question mark info. The last line in this particular record says that persistence information is unavailable. The question mark info ending is an example of an ARK inflection. An inflection is a grammatical device to modify the meaning of a word by making small changes to the end of the original word. One advantage is that you don't have to assign and manage completely separate identifiers both for the object and for its metadata. Instead, just inflect the original ARK. There's been a debate about requiring PIDs to cite a landing page rather than a directly usable PDF, image, spreadsheet, etc. It's a painful choice. It is often seen as if either you give up metadata access or you give up direct PID access to content by sending everyone to a landing page. Both outcomes are kind of terrible. This is only hypothetical for ARKs so far, but imagine if we could standardize inflections for a landing page versus plunging page. Every server can already provide either experience, so why not add a way for users to ask for each experience explicitly? The server could be queried to return for a given identifier, either a landing page experience or an immersive sub-landing page experience. This seems like the best of both worlds. This use case describes the YAMS.NET system that is supported by the Metadata Research Center at Drexel University. Note that the nan here is more than a number. It has extra characters on the end, namely /h1. This kind of extended nan is known as a shoulder. ARKs are useful for vocabulary terms or concept IDs because any investment in linked data is more protected with permalinks. Concept IDs are good for things like spreadsheet column header names or variable names, control values under those names, relationships, pick list values, and so on. Thousands of work groups across the world are inventing vocabulary or modifying existing terms, but they don't have easy ways to share and get feedback on changes. YAMS was created by Dublin Core metadata insiders who saw a need for an aggressively domain-agnostic tool that helps people share, discuss, and reach consensus quickly on whatever metadata profile they're working on. So we built a crowdsourced metadata dictionary called YAMS. It lets anyone look up terms to reference. You can log in to comment on other people's terms. You can also upvote or downvote terms and watch them so you get notified if they change. This term is labeled vernacular class, which means it can be changed by the owner, but terms labeled canonical class are done changing. There are also deprecated terms, but they too will always be available because historical documents will be available. You can add your own term and immediately walk away with an ARK persistent identifier to reference it. There's no problem creating multiple terms with the same name string. This one has 13 alternates, but each alternate will have a unique ARK concept identifier. You can also add tags to terms and import terms in bulk via a CSV file. In case you were wondering, when would there be a slide on philosophy? Well, here we go. Let's consider what a persistent identifier string represented by these 26 characters can tell us. Is it data? Is it an identifier? Is it an opaque identifier? We don't know much by looking at it, but it's useful if someone associates it with something. An identifier is really an opinion. It depends on who you ask. In other words, on which name authority you ask. If it is an identifier, it would be terribly helpful if it were inside a URL, such as this one. That's because the domain name early in every URL is actually a name authority. And the HTTPS out in front means we can query the authority implied by that domain using a web browser. When we do that, what comes back is a web page explaining that this string is an example identifier. What we won't see is that behind the scenes, the browser received a 404 not found error. So this modified string looks like a URL, but even though the browser displays a page, according to the official query status, it is not an identifier. Maybe someone else has an opinion. Let's change to a different authority, in this case, the doi.org domain. This third string looks like a proper PID. In fact, it's a DOI, right? Well, no. When we click on it, we see a web page that tells us a 404 not found error occurred. The DOI system has no knowledge of it, and so even though it looks like a PID, it's not a valid identifier. Okay, so let's try again, but using a different subauthority within the doi.org domain. This time our browser returns a web page with no 404 error. So now we have a true valid DOI, so this should identify trustworthy, citable, scholarly content, right? Wrong. In fact, it identifies a kids movie. That's because it was created by a registration agency that assigns a DOI to every movie made in the United States. The point is that you can assume very little about an object or its persistence by looking at its so-called persistent identifier. If it looks like a PID, that is only a suggestion. What you get back also depends on what you ask, and when you ask. The query experiences described for this slide were made in early 2024. Persistence is not conferred by a string, prefix, or syntax. That's true whether you're dealing with ARKs, DOIs, handles, URNs, or any URL-based permalinks. Tools for implementing ARKs can be found in the resources area of the ARK Alliance website. They include minters for generating unique opaque strings, for resolvers, plugins, and an ARK service for library administrators, and the list keeps growing. Suffix pass-through is a feature that a web server can choose to support in order to greatly increase the number of identifiers that it can forward. It dramatically reduces the burden of maintaining identifiers by permitting one identifier to stand in for millions. The way it works, given a URL for the stored identifier, if an ARK arrives with an appended suffix, N2T will reappend it, pass it through to the destination during resolution. This is critical for IIIF applications so that the many addressable subparts and formats don't all have to be separately registered, maintained, and possibly paid for. This final case study uses a visualization from Dave Igles of the U.S. National Science Foundation iSamples project. It allows us to visit the South Pacific island of Moorea in French Polynesia. Each of the colored points represents a physical sample, and the towers indicate that many samples were collected at the same location. Each sample point has an ARK identifier, which is displayed when mousing over it. Clicking on one of the points brings up summary metadata, which allows you to link back to the original collection. Following that link to the Smithsonian, you can find more details about the specimen with cross-references to analyses, publications, and other material. The interlinking is done with millions of ARKs, and the number of participating collections should grow significantly as the project continues. It's all part of the NSF iSamples project, which assigns identifiers to biological specimens, rocks, and archaeological artifacts. So in conclusion, what do 10 national libraries, 145 universities, 184 archives, 90 museums, and 75 journals all have in common? They are all registered to use ARK persistent identifiers, open, mainstream, non-paywalled persistent identifiers that you can start creating in under 48 hours.